Okay, hi everybody and welcome to my channel Art and Physics. Well, in this video we will find the equations of motion of the mechanical system shown on the screen using Lagrangian dynamics. Well, the system is basically formed by two objects. The first one is a cart of mass capital M which can move horizontally and is also connected to a fixed point by means of a spring of stiffness capital K. The second object hangs from the first one by means of another spring of stiffness K and natural length L. It is worth to mention that this second object has also mass M. So in the Lagrangian equations shown also here on the screen, the main term, the principal term here is well, obviously the Lagrangian L, which is actually also equal to the kinetic energy of the system, capital T, minus its potential energy, capital B. The other terms here, the Q sub I, are the generalized coordinates of the system, which are the minimum set of coordinates that can completely describe the motion of the system. Well, in our case, we will use the following coordinates. First, we will use x as the horizontal displacement of the first object. We will use also the angle theta, which is formed by the direction of the second spring with respect to the vertical line, and u will denote the extension of the spring measures from its natural length. So we'll have three generalized coordinates. I will note it here. Will be q sub 1 equal x, q sub 2 equal theta, and q sub 3 equal u. Three generalized coordinates, so 3 degrees of freedom. So let's first begin by writing the Lagrangian, and let's first focus our attention in the kinetic energy. This kinetic energy can be divided in two components. First, the kinetic energy of the cart, which I will call T sub 1, which is actually equal to simply 1/2 capital M times x dot square, being x dot the velocity of the cart, and T2, which will be the kinetic energy of the second object. This is a slightly bit more complicated, but we will need first to write which is the velocity of this second object. So let's do another drawing here. I will draw here the second object, the second mass, and in order to find its velocity, we can think as follows. Let's first assume that this first object is frozen, it's completely still. Then we can use polar coordinates to express the transversal and radial velocity of the second mass. Note that the distance between the first object and the second object is equal to L plus U. Why is that? Because L is the natural length of the spring and U is its extension. So the transversal velocity, I will use blue, will be equal to L plus U times theta dot, and the radial velocity will be U dot. But we should not forget that the cart from which hangs this second object, it's also moving with velocity x dot, so we have to add it here to our second object, x dot. Thus, the total velocity of the second object is equal to the vectorial sum of these three velocities. It's good to add here the angles. This is theta. This is also theta. So we can write the velocity of the second object, I will call it b sub 2, summing in horizontal component and vertical component. In the horizontal direction, we have L plus U theta dot cosine of theta plus U dot sine of theta plus x dot. And in the vertical direction, we have L plus U theta dot sine of theta, and now minus U dot cosine of theta. This is then the velocity of the second object. We need its kinetic energy, the term T sub 2. And in order to find this kinetic energy, we need to also find the square of the speed of this second object. In order to find the speed, we will need to raise to the power of 2 the horizontal component, sum it to the square of the vertical component, and then take the square root. The square root will vanish because we will need to find the speed square. But the problem of summing these two components square looks at principle a little bit cumbersome, but we can do the following in order to simplify our lives here. Let's call A this first two term, and let's call B these other two terms. So if I will find the if I need to find the square of the speed of this second object, we need to square the horizontal component, which will lead to the following: plus x dot square, and then sum the square of the vertical component. It's easily to see what will happen if we put these two terms here together, which is then the following expression. And we can look closely to what will happen to E squared plus B squared. If we look the expression for A and B, we will note that when we square these two binomials, the term square, the L plus U square times theta to the square times cosine square will be simplified using the Pythagorean trigonometric identity. You know, cosine square plus sine square is equal 1. So these two terms here, ax square and b square, will lead to the following. First, we'll have L plus U square times theta dot square, nothing more, because again, cosine square plus sine square is equal to 1. Here, a similar thing will happen. The result will be just U dot square, because again, trigonometrical Pythagorean identity. And if you look closely, the double products will also vanish. We will have 2 times this this U dot sine theta will be vanished with this minus 2 L plus U theta dot sine theta plus times U dot cosine theta. So these two terms will vanish, and the next terms are basically the same. Here not much will change, so I will write it again like so. Okay, that's it. Then the square of the speed of the second object. So we can write our kinetic energy as the sum of the kinetic energy of the card plus the kinetic energy of the second mass. It's a big expression here, so let's write it. Times 2 L plus U theta dot cosine of theta plus U dot sine of theta, all this multiplied by x dot, finally plus x dot s square. Okay, here we have it, the kinetic energy. But we need also to find the potential energy, B, capital D. The potential energy in this case of this mechanical system can also be divided in 2 components: the elastic potential energy stored by these 2 springs, and the potential gravitational energy, which is due to the vertical motion of this second object. The potential elastic energy is fairly easy. Again, just 1/2 capital K x squared plus 1/2 k u squared. But what is the potential gravitational energy? We need to define first a level of reference for the potential energy. We will use in this case the situation in when both u and theta are 0. This will be our level of reference, our 0 potential gravitational energy. When the system is perturbed, when this mass is in motion under an angle theta and an extension u, let's call this u, then the center of mass of this second mass will change as follows. First, it will ascend, go up, in an amount of L1 minus cosine of theta, and then we can think here it's also descending in an amount of u cosine of theta. So the total ascent of the second mass, center of mass, is this minus this. Thus we can write the potential gravitational energy as follows. Let me do if I'm not wrong, we can factorize all these in just one step. This is the same, right? It's the same. Okay, so we have it. We have kinetic energy and potential energy. Let's then begin by setting the equations of motion of our mechanical system. And let's begin with the first generalized coordinate, which is x. If we look again the Lagrangian equations, we will note that first we need to find the partial derivative of the Lagrangian with respect to the first generalized velocity, also to x dot. We need to find then this partial derivative. And the x dot term only appears in the kinetic energy. Well, it cannot appear in the potential energy, because in order to have a potential energy, it has not to depend in the velocities. It's only dependent on the position, so we can never have velocities here. So let's derive the kinetic energy with respect to x dot. The first term is fairly easy, m times x dot. Then we have this big boy here, is which this whole parenthesis, which is multiplying x dot. There's also a 2 here, which will be cancelled with 1/2. So we have m times all this expression here. Plus u dot sine theta. And finally, the derivative of this term, with respect to x dot, which is, 2x dot multiplied by 1/2 m, is just simply mx dot. Okay, again, now we need to find the total derivative with respect to time of this later partial derivative. Here things will turn a little bit more bigger, but there are two terms fairly easy. Again, this will be in this first and last term, just this expression, and now we have to derive all these parentheses here. But we have here this triple product of functions of time. L plus u is a function of time. Well, u is a function of time. U dot is certainly a function of time, and also cosine of theta. Let's say that this is the first function, the red one, and this one is the green one. Okay, so we need now to apply the product rule for derivatives. So let's first derivate the red term, just u dot, times the green one, plus red term, red function, times the derivative of red one, which is first again the product rule, theta 2 dot cosine of theta, And now the derivative of cosine of theta, which is minus sine of theta times theta dot. Chain rule here. Minus theta dot square sine of theta. Okay, plus the derivative of this term. I will need more space here, so I will continue below. U 2 dot sine theta plus u dot theta dot cosine of theta, closing this big parenthesis here. Okay, so we have here the total derivative with respect to time of this term. Okay, which is also somehow like the momentum of this, in this case for x. Perfect. What we need to do now, we need to, I will go back to the Lagrangian equations. We need to now calculate the partial derivative of the Lagrangian with respect to x. We need to find this value. And again, let's look closely to the expression of kinetic energy and potential energy. The term x, where does appear the term x? Well, luckily for us, does not appear in the kinetic energy, only in the potential energy. And not forget that the Lagrangian is kinetic minus potential. So the derivative here will be, I have a minus sign. In this case, it's just minus kx. We are almost ready with this first equation. So the first equation of motion, a little bit somehow big equation, but this now just we just need basically to write it all again. Here I will write it again. This is somehow boring, but in order to leave all the expression completely here. Again, not enough space. Minus the partial derivative of the Lagrangian with respect to x, plus kx. Well, equals 0. It's equals 0 because we are assuming there are no non-conservative forces present in our system here. Well, I will leave this video for now here. I will continue this with the other two generalized coordinates, which are namely theta and u, but the procedure is similar, it's the same. We need to find the partial derivatives and set our equations. These are the nonlinear equations, and maybe in a future video I will talk about the linearization process, in which all these nonlinear terms, these trigonometrical nonlinear terms, can be simplified and in order to obtain a linear equation. Okay, so well, that's all for now. I hope to see you again in the second part of this video. So I hope you enjoyed the video. This is a fairly new channel. I'm just beginning to this, so I hope you like it. Any question or comment, just feel free to tell me. Okay, so bye bye.